Welcome all. This is part B of concept video for 1110. Earlier we saw the representation of a function by Taylor series, which is centered at A. How to represent a function by means of Taylor series. This is around A. And then next we saw Maclaurin series, which is derived from Taylor series. This is centered at 0. That is the difference between the two. And then we saw an example how to represent e to the x in terms of Maclaurin series. So now we will see how to represent the same function e to the x as Taylor series at a equal to 2 by means of Taylor series at a equal to 2. Only when it is a equal to 0, it is called Maclaurin series. For all other values, it is said to be Taylor series. So let's try this one using that formula that we derived. So first, we have to write the Taylor series representation. F of x equal to e to the x equal to, if you write this in sigma form, it is sigma nth derivative at a, here a equal to 2, a is given to be 2, divided by factorial n times x minus a is equal to 2 to the power n. This is the representation, Taylor representation of, Taylor series representation of the function. Centered at about a equal to 2 or centered at centered representation about a equal to 2, or you can say centered at 2. Either way, both are right. Now you can, if you want to write the expanded version of this, it's going to be, the first one is f at 2 plus f prime at 2 over factorial 1 x minus 2 plus second derivative at 2 over factorial 2 x minus 2 the whole square and so on. If you want to write the generic term, it will look like nth derivative at 2 divided by factorial n x minus 2 to the power n, goes on like that. So we are going to find out all these values f at 2, f prime 2, etc. for this expression for the function f of x. That will be our next step. If f of x is e to the x, so by the way, we this step is actually from the formula that we derived earlier for Taylor series. Here in this problem, it is centered at a. Now we are using a equal to 2. It is coming from the step. So f of x equal to e to the x. So f at 2 would be e to the 2. Then let's try the derivative. All the derivatives are going to be the same. F prime x is e to the x, and its value at 2 is e square. Then the second derivative is also e to the x, and the second derivative at 2 is e square. So like that, all the derivatives at 2 is going to be e square. So remember that when we said nth derivative like this, if you write superscript with the parentheses, then it means the nth derivative. That's another way of writing. Instead of putting double prime, triple prime like that, we use this shorter version of it. So substituting them into the function f of x equal to e to the x, f at 2 is e square plus e square over factorial 1 x minus 2 plus e square over factorial 2 x minus 2 the whole square. Generic term will be square over factorial n, x minus 2 to the power n, and it continues. So we substitute all these values into n1. And then we are going to, as usual, we are going to find out the radius of convergence for this. Also, this can be written in the sigma notation, sigma n varying from 0 through infinity. We are looking at this step. If we write like this, it is sigma n varying from 0 through infinity. Nth derivative at 2 is e square divided by factorial n x minus 2 to the power n. Just the way if we found out the radius of convergence for the earlier Maclaurin series, if you when you find out the radius of convergence, we will use the ratio test. So the ratio test would be a sub n plus 1 over a n, nth term, n plus first term over the nth term. That will be here e square times x minus 2 the power of n plus 1 divided by n plus 1 factorial. They are dividing by an, so you take the reciprocal and multiply. It's n factorial divided by e square times x minus 2 to the power of n. So e square in this, e square get cancelled out. Then this one x minus 2 to the power n. Here x minus 2 to the power n plus 1, that gives us x minus 2. Then this one will give us n factorial. This will be n factorial times n plus 1. So factorial n cancel out. That gives us n plus 1 in the denominator. So we are left with x minus 2 on the numerator. On the denominator, it is n plus 1. If you take the absolute value and allow n to approach infinity, limit n approaches infinity, because of the presence of n in the denominator, so you have something divided by infinity, this will become 0. But ratio test tells us that whenever this limit is less than 1, the series is absolutely convergent and hence converges. So by ratio test, we can say the Maclaurin series, here the Taylor series, f of x equal to e to the x, x minus 2 to the power n converges for all x. And the radius of convergence is equal to infinity. So here we have seen two problems. One was Maclaurin series for e to the x. Both are for e to the x, function e to the x. Then one was centered at the origin, which was called Maclaurin series. Then the radius of convergence turned out to be infinity. And we saw the representation of e to the x as Maclaurin series. Next one, we found out the same function centered at a equal to 2, centered at 2, that was Taylor series. And here also the radius of convergence was infinity. So whenever we have two part series representations for e to the x, the Maclaurin series and Taylor series. The first is better if we are interested in values of x near 0, because Maclaurin series is centered at 0, then the second is better if x is near 2. So let's try the next example. Find Maclaurin series for sin x. Maclaurin series for sin x. So that is step 1. So what is Maclaurin series? We will write that and then we will figure out what each term is. So f of x equal to sin x, which is, because Maclaurin series is centered at 0, it is f at 0 plus f prime 0 over factorial 1 x, f double prime 0 over factorial 2 x square. It goes like this. Nth term, nth derivative at 0 over factorial n x to the power n, and it goes on like this. We write the same thing in sigma version. It is sigma n varying from 0 to infinity, nth derivative of f at 0 over factorial n x to the power n. So we are going to find out these coefficients, namely f of nth derivative of f at 0 for all values of n. So let's start f of x, which is sin x, and f at 0 is sin 0, which is equal to 0. What is the first derivative? Derivative of sin x is cosine x, and its value at 0 is cosine 0, which is equal to 1. And the second derivative, negative of sin x, which is f double prime at 0, which is negative sine 0, which is equal to 0. The third derivative, negative cosine x, and third derivative at 0 is going to be negative cosine 0, which is equal to negative 1. Because we have some of the values 0, some of the values plus or negative 1, we will derive a pattern by looking at few more derivatives. Fourth derivative at x is negative of negative sine x. So it will be sine x. So fourth derivative at 0 is sine 0, which is equal to 0. And the fifth derivative at 0 is cosine x. Then you try that at 0, which is cosine of 0, which is equal to 1. What about the next derivative? This negative sine x. So sixth derivative at 0 is negative sine 0, which is equal to 0. If you notice the pattern, the first, third, fifth, seventh, all these terms are 0. Alternate terms are 0 starting from the first term. From the second term onward, second term is positive 1, and the fourth term is negative 1. The sixth term is positive 1, then the eighth term would be negative 1. So if you just try seventh derivative, just for one more, is negative cosine x. Seventh derivative at 0 is going to be negative cosine of 0, which is equal to negative 1. So the even terms alternate in sign, it's plus 1 or minus 1, just the derivative part. So putting all this together back into this expanded version, so f of x, which is equal to sin x, becomes substitute the values from the table into step 1, we get f of x, which is equal to sin x, The first term f at 0 is 0, then f prime 0 over factorial 1. So 1 over factorial 1 times x. Then you have next term 0, the next term is negative 1 over factorial 2, factorial 3, x cube. Then you have positive x to the power 5 over factorial 5, then minus x to the 7 over 7 factorial. It goes on like that. If you give a precise version, um, symbolic representation in sigma notation, so you notice that you have alternatively positive and negative, the first term starting with the positive, and also if you look at the exponents of x, they are all odd numbers. So if you have to write that in a concise form, then it is sigma n varying from 0 through infinity, negative 1 to the power n, x to the power an odd number. You already saw that whenever you want to represent an odd number, it is either 2n minus 1 or 2n plus 1 divided by 2n plus 1 factorial. Then one more thing is needed to be proved. So this is the representation. This is the Maclaurin series representation of sin x. So how do we then prove the radius of convergence? That needs to be done as well. So step 4 is to find the radius of convergence. MDR of C. So we, as usual, will apply only ratio test for this. So we will do an plus 1 over an. So an plus 1, from what we have written here in the step, without the sigma, that will be our nth term. So we can write that. That is negative 1 to the power n plus 1. I'm writing the n plus first term. So it is x to the power 2 times n plus 1 plus 1 divided by 2 times n plus 1 plus 1 factorial divided by negative 1 to the power n, x to the power 2n plus 1 divided by 2n plus 1 factorial. So if we reduce this, negative 1 to the power n plus 1 over negative 1 to the power n, that will give us just negative 1. Then the rest of them we will rewrite. It is negative 1 times x to the power 2n. If you distribute it is plus 2 plus 1 to 2n plus 3 divided by denominator is 2n plus 3 factorial. Again same thing, 2n plus 2 then plus 1 with the factorial notation. Then if you multiply, if you take the reciprocal and multiply, you will get 2n plus 1 factorial divided by x to the power 2n plus 1. Just the way we did the usual trick in order to cancel out the factorial terms, this can be written as 2n plus 1 factorial times 2n plus 2 times 2n plus 3. So the 2n plus 1 factorial would cancel out, and x to the power 2n plus 1, x to the power 2n plus 1, that will give us x square. So you are going to write absolute value and then take the limit. Limit as n approaching infinity of absolute of the ratio of the n plus first over the nth term. So it will be limit n approaching infinity absolute negative 1 x square divided by 2n plus 2 times 2n plus 3. So it's going to be, as again in this one, the denominator is 2n plus 2 times 2n plus 3 as an n approaching infinity. the denominator would approach infinity. So it is irrespective of the value of x, this limit is going to be 0. So by ratio test, it's a limit equal to 0, less than 1. So it converges for all x. So by ratio test, sin x, which is equal to which is written as sigma negative 1 to the power n x to the power 2n plus 1 over 2n plus 1 factorial converges for all x. In other words, radius of convergence equal to infinity. This representation for sin x is the Maclaurin series representation for sin x.